Hello and welcome. This video is going to be a super exciting video because this week I actually finished my second data science book in my data science journey. I've been trying to learn data science from the very beginning, from scratch, for the last, I think this is the 16th video, so it would be 16 weeks. And in those weeks, I have, day in and day out, have been studying, and it looks like we are getting somewhere. And it is only a little bit halfway through the 6-month challenge that I gave myself, in early April-ish time period. So I am well on my way. Like I said, this video is exciting because I finished my second book, Thinkstats, and in this book I learned everything from introductory stats to pandas to numpy to scipy and almost everything needed to visualize and create graphs in Jupyter notebooks, and the plethora of theorems and different methods of looking and thinking about your data and all that. But before I give a really in-depth review of the book, let me just give you the shortened version of this video so that you can peace out and say goodbye if you want to. If not, you can stay for the rest of the video. So the shortened version of this video is I happen to finish my second data science book. I happen to do chapters 13 and 14. Chapter 13 was on survival curves, and chapter 14 was basically just a wrap-up of the book, but also a little bit about the difference between analytical and computational methods, and a little bit on normal distributions. So that's basically it for my little summary. Now, the long version of this is actually that in chapter 13, I went into depth on survival curves, and survival curves reminded me a lot of the the geometric curves in stats. In stats, you have the geometric curves, which are the first success in a series of Bernoulli trials, and survival curves really reminded me of that because, for example, we're looking for as an example, the longevity of the human race. So let's think of, or like, when someone is gonna die. I'm gonna choose a better example, but very simply, we're looking at the success. Is someone alive at a certain age, or a failure, which is a death at a certain age? And that creates a very nice curve, as most people tend to die when they're older and not when they're younger. So, like I said, it reminded me of the geometric curve in stats. And actually, to go into more in depth, I'm gonna choose a better example because talking about people's mortality like that is just not great right now. So I'm gonna think of a better example. Okay, so as another example, we can look at the survival rate of a female getting married. Now, we'll think of getting married as a success and unmarried as a failure. Now, if we have a label like that, as success and failure, it could be a Bernoulli trial, and then it relates very well to a geometric distribution. But for now, we're talking about the survival, and you can have data of a bunch of unmarried females, and then you can have the data of a bunch of married females, and you think, okay, so I'm trying to look at when people get married, right? That's the survival rate, how long it takes for people to get married, and when they get married, they die off, right? Now, funny enough, a lot of people would think about getting just the data from the married, look at the age, and create the curve from that. And that would be a terrible idea because it would be super biased. It would be looking at all the women, all the females that have get married. So all of those are successes in the end. You just successes at different ages. So funny enough, that would create very biased data. So we do need to include a data set of unmarried females in this survival curve when we're trying to make it. Now, funny enough, someone's already figured out how to do this. There's actually a method called the Kaplan estimation, and using this process, you can basically find a way to put those two together and actually create a single survival curve for, females getting married. And you can then use that curve to infer at a certain age when someone, or what the probability is of them getting married. Again, as a success or failure. So, in this case, a marrying is actually a success. So you can look at it any way you would like. So that was chapter 13. And chapter 14, like I said earlier, was just a little bit about the difference between the computational and analytical methods in the book. I mean, in the beginning of the book, I went over this. The book really places a very deep emphasis on computational methods, since we could use the computer to generate a lot of trials for us. Instead of just believing the theory, we can actually do the theory. We can create the theory. We can use a random number generator. We can use code to run a loop and just create our own population, create our own sample, and do all of that with just a couple lines of code. So that is how the author decided to teach us statistics. Now, there's already been a lot of work done in this field, so there's actually already some analytical models, which is what you learn in school, right? And it can get kind of confusing sometimes because you've never seen them played out. So again, that's why the author decided to do it this way. But in the chapter 14, we actually went over a couple of analytical methods and how sometimes they can be way easier than just actually doing the computational heavy method. So for some examples, for example, the normal curve, we can use p-values very quickly. The difference between the normal curve and the other things that we went over is that, when you have a normal distribution, you're looking at the area under a curve as the z value, and then you find the p-value from that. And that area under the curve is, very different from, it makes it impossible to basically do a PMF, which is a probability mass function, because there isn't just one point. It's the distance up to that point in the graph. It's basically the area under the curve. So due to that, there's actually an analytical method, like I mentioned, the z-score, then looking at the p-value table, that will make this computationally very easy and an instant find. You can even use just pen and paper to figure it out. You will need the printed out p table or z table, but it's fine. Now, he also went a little bit over normal distributions here, since he was on the topic. He also went over a little bit what the central limit theorem means, and if you don't know what that means, let me explain it to you. Central limit theorem is basically when you have a population, and this population doesn't have to be normally distributed. It could actually be a little bit skewed to the left or the right. And actually, if you were to get a lot of samples from that population, and then you were to find the mean and the standard deviation, and then you were to get, together all those different sample means and standard deviations, you would actually end up with a normal distribution right then and there. And this is actually just due to nature and the way nature works, but it's a very cool theorem, and you can use it and apply it a lot to many things. And it's just kind of a cool thing that we figured out. And when it comes to using it, there are a couple of caveats. You want to make sure that the data actually isn't too skewed. If the original population is crazy skewed, you're going to have to take a lot of sample means to really kind of get it to be normal. But for the most part, it works. There's a lot of other caveats that you want to make sure while you're doing your calculations, but I don't remember them, but you can find them online easily when you do decide to use central limit theorem. Found that really cool. And yeah, so then he just wrapped up the book. I found this book to be fantastic. It got a little boring at times for sure, but I am super excited because this gives me the most amazing fundamentals when it comes to an EDA. I now know the steps of conducting an EDA. Let me explain what an EDA is. An EDA is exploratory data analysis. So it really is just, when you get your data, you go through it, you learn from it, right before you get the computer to then learn from it, you know, more advanced data science. But this is basically the fundamentals we're talking about. So, we learned pandas, we learned numpy, scipy, we learned how to make graphs, we learned Jupyter notebooks, we learned the steps to conduct, exploratory data analysis. We learned how to fill in null values or NaN values, number not available. We learned how to, use a couple different stats ideas like PMFs, CDFs. We learned a little bit about, central limit theorem, chi-square test, normal distributions. We learned about, oh my gosh, what else did we learn about? We learned about survival curves. We learned about, man, the list really goes on and on of all these things I learned that I can now pull from my memory. And I am actually thinking of, creating a little Anki of all the different definitions that I learned from this. It's really not necessary for me to memorize them all, but just to know that they exist. So actually, better than an Anki deck, I'm actually going to create a little tree of knowledge that, I might post in the description. I'll use a large piece of paper and I'll draw out a large tree of knowledge that I learned from this book, specifically the steps to do an EDA, which is super cool and super necessary. All right, so I hope you enjoyed this in-depth look of my learning path, and I'll see you guys in the next video. Peace.